Today we will continue our lecture on friction. In the earlier lectures we saw simple contact friction where the geometry of the contacting surfaces was simple. So, computing the friction and the normal forces were to some extent easy. For contact surfaces which have complex geometry, we have to consider small elemental areas and write the friction and the normal forces for those differential areas and then integrate their effects in order to arrive at the overall effect of friction. Today our discussion will be on one such interesting problem on square threads. Square threads are used for screws used in the jacks and in presses and for clamps. The main purpose of these devices is to hold components or in case of a jack to raise the load. The friction between the threads are advantageously used to do the required function. So, in this picture you see a jack which is typically used to raise the automobiles for doing repair work. So, the automobile axle is supported on this cab. So, this W represents the weight of the automobile that is carried by this cab of the screw, and this is the square thread and this is the base in which there is a mating square thread. So, the automobile workshop person applies force on this lever in order to rotate this screw and thereby to raise or lower the screw and thus the car body. The friction between the thread and the mating face on the base has to be overcome when raising this load, and if we want the raised load to be kept in the place, then the friction here should be sufficiently large to prevent this screw from unwinding if this force is removed from the lever. So, the design of this screw jack is essentially based on the condition that the force required to raise should be minimal as well as the friction should be sufficient enough to prevent this screw from unwinding. So, let us see this geometry of the screw. Let us consider a portion of this screw. So, these are the threads. These threads have an angle of inclination, say alpha, and the screw cap supports a load of W. the effect of this force P is to produce a moment required to rotate this screw. So, it can be replaced by say a moment mz, where mz is equal to P times of A, the moment produced by this force about this axis of the screw. Let us consider the mean radius of the threads as r. So, here r is the mean radius of the screw. The distance between two successive threads along the axis of the screw is known as the pitch of the thread. So, for a single threaded screw, the pitch is equal to the distance that a nut will travel when it completes one revolution. But there are threads which have multiple starts, where the advancement of the nut is equal to, let us say if it is a 2 start thread, then we have 2 times the pitch. So, if we designate P as the pitch and L the lead, that means the amount the nut moves on the thread, this L is equal to N P, where N is the number of threads. From the geometry, we see that the distance moved by the nut, which is L, is related to this angle by this relation, because when we move by a distance of 2 pi r, the load is raised or lowered by a distance L, and so this angle is tan inverse of L by 2 pi r, or it is equal to N P divided by 2 pi r. So, now that we understand the geometry, let us see where these frictional forces come into play. On these thread faces, the frictional forces act along this thread face. So, if we tend to move this screw in this direction, the force of friction offers resistance, and thus the direction of the frictional force will be in the opposite sense, and this will be the normal force. Let us say dN and dF. dF is this frictional force and dN is the normal force. These forces can be assumed to be acting at a distance of r from the axis of the screw, because the width of the screw threads is very small. So, these forces are acting in the entire circumference of the thread, and all these forces are having same direction cosines with respect to the axis of the screw. So, we can consider an equivalent free body diagram where we represent the sum of all these frictional forces and the normal forces by a single force F and N, but one should remember that this is only with respect to the axis of the screw. So, let us consider that free body diagram. Let this be the screw. We have the weight and the applied moment, say mz. This is the sum total frictional force acting on the thread face, and this is the sum total normal force acting on the thread face. So, this free body diagram is an equivalent free body diagram that can be considered for arriving at the relation between the applied moment and the frictional forces for the z direction. One should remember that we cannot use from this, let us say, the relation sigma fx or sigma fy. These cannot be used. So, now let us write the equations that the sum of the forces in the z direction has to be 0. From this we have minus w plus n cos alpha, this is also alpha, minus, for the impending slippage case we have this frictional force F related to this n by this coefficient of static friction mu s n sin alpha equal to 0. Then we can sum the moments of these forces with respect to the z axis and equate it to 0. So, we have minus mu s n cos alpha r, which is the moment of the component of this frictional force in the horizontal direction, minus n times sin alpha dot r, which is the moment of the component of this force n in this direction. This is the circumferential direction. The line that is shown in this figure is for taking the components of these forces that are tangential to the circumference of the thread, and they cause a moment that has to be balanced by the applied moment, plus mz, which is the applied moment, has to be 0. So, if we solve these two equations and eliminate this n, which is the unknown, we have mz equal to w r mu s cos alpha plus sin alpha divided by cos alpha minus mu s sin alpha. So, this is the moment that has to be applied in order to raise the load. Now, if we are interested to know whether the screw jack will unwind if the force is removed, or we call that whether a screw jack is self locking. That means, once we remove the applied moment, if the raised load is maintained at the same position, then we call it as a self locking screw, and if it unwinds, then it is not a self locking screw. So, if we want to know the condition or the minimum frictional force that is required, then in this equation we put for this self locking condition, we put mz equal to 0, and since it is unwinding, the direction of this frictional force has to be reversed, that is, it will be acting in this direction when the screw tends to unwind, and reverse the sign of F and solve. So, if we do that, we will find that the minimum frictional force or the minimum coefficient of friction that is required is equal to tan alpha. We already know that mu s is can be represented by an equivalent frictional angle. So, now we have a relation between the angle of friction and the lead angle of the screw. So, if this mu s is less than tan alpha, then it is not a self locking screw. If mu s is greater than tan alpha, then it is a self locking. Let us see one example problem for solving the required friction in a square threaded screw. So, here you see a vise which is supported on to a platform, one of its jaws is supported and the other jaw can be tightened or loosened using this screw. The mean radius of the screw and the coefficient of friction is given, and we are interested to find the force that is being exerted when a 60 Newton meter torque is applied to the screw. Here we see that these jaws are pinned at D, and at B this screw is free to rotate. So, let us consider the free body diagram of this screw and the jaw. So, let us draw the equivalent free body diagram for the screw, where the equivalence is valid for the axis of the screw. So, we have this screw, and on this face there is a uniform reaction because of this jaw CB. So, let this total reaction be N1. The equivalent frictional force and the normal reaction on the face of the threads at this point A can be represented by this single forces F and N, which are inclined at an angle alpha, which is the lead angle of the screw, and we have the applied moment M, which is 60 Newton meter. Now, if we consider the free body diagram of this jaw dA, at D it is supported by a pin. So, we have dy and dx, the two components of the reaction, and at A we have the equal and opposite forces. So, we have this normal reaction and the frictional force F, and we have this force P. The dimensions are known. So, from these free body diagrams we can now write the required equations to solve. Let us consider first the free body diagram of the screw, which is shown here, and we can write the moment summation equation and force summation equation along the screw. We have already seen that in this equivalent diagram we cannot write the summation of the force in the x or y direction. So, if this is the z direction, then we can write the force summation along this axis and moment summation of these forces about this axis. So, let us write the equation. Before computing, let us find the lead angle, which in this case is tan inverse of 3 by 2 pi r, which is 12 mm. So, the lead is equal to pitch and it is equal to 3 mm and the mean radius is 12 mm, and from this we find the angle to be 2.279. So, let us write the force summation about this z axis, so which is n cos alpha minus mu n sin alpha. For the impending case, this frictional force is equal to mu times n minus n1, the total reaction on this face, and we equate it to 0. Let us sum the moments. We have this applied moment, which is minus 60 Newton meters, plus the moment due to this frictional force and this normal force, which is n sin alpha dot r, the mean radius of the screw, plus mu n cos alpha times r, and this has to be 0. So, from this we get, knowing this value of mu as well as this alpha, we find n is 26364 Newton. Here we are not using this equation, but if we are interested to know the reaction, then we can use this equation to find n1. So, now let us move to the next free body diagram, that is the vice arm, and this shows the free body diagram. Here we have already computed this n, and so now we can compute this force P if we take a moment equation about this point D. So, let us write that equation. So, summing the moments about D and equating it to 0. So, we have the load P times the moment arm, which is 600 mm, so 0.6 meters, minus this force N cos alpha, which is the vertical component, and the vertical component of this force is plus mu sin alpha, and both of this have the moment arm of 0.45 meters. So, we can say times 0.45 equal to 0. So, from this we obtain P as 19.64 kilo Newton. So, this example illustrated the method used to solve for the square threads. We can determine the required unknowns by considering the equivalent free body diagram. We will see another method of analysis where the analysis of this thread is made as a problem of solving the inclined plane. So, let us see that. This is the screw jack that we have considered earlier. This problem is now converted to a problem similar to that of a block on an inclined plane. If we unwind the thread and put it on the plane of the screen, then the problem can be considered as raising a load along this incline. So, this picture shows the unwrapped thread. We know that when we move along the thread by this distance 2 pi r, the thread raises by the lead distance. So, if we complete one full rotation, this load is raised by a distance of L. So, it is equivalent to saying that we raise this load W on this inclined plane. The force applied on this lever arm, which is the moment that is required to rotate this screw, is represented by an equivalent force Q, which is used to raise this W on this inclined plane. this theta is the lead angle of the screw. Now, this problem can be solved by using the free body diagrams that are derived from this equation. So, the problem of finding this Q is simple, because the moment of this force P is equal to the moment of this force Q which is applied on the circumference of the thread. So, if this is the mean radius r, then Q is the force. So, we are considering the thread in the as viewed from the z direction, and we have the applied moment of this force which is P times of A. So, the force Q should be large enough to resist the moment due to this lever. So, which is P A. So, from this we can find what is Q. So, once we know the Q, we know the required quantities and we can solve the problem using the plane analogy. The problem of analyzing the self-locking behavior can be considered for the inclined plane analogy also. So, if we have the impending motion upward, it is equivalent to raising the load by applying the required moment on the screw jack. So, this is the equivalent free body diagram of the inclined plane. The reaction force, which is the sum total of the normal reaction and the frictional force on this face, makes an angle of phi s with respect to this normal, and if theta is the lead angle, then the normal of this inclined face makes an angle of theta with this vertical. If the thread is not a self-locking thread, then a force or a moment has to be applied in order to lower the block. The analysis of the screws that we have seen can be done by another method, where we analogize this problem to that of raising the load on an inclined plane. So, let us consider this screw jack again, where we apply this force P to cause a moment to raise this load W. We draw an equivalent inclined plane by unwrapping the thread on the plane of paper. So, we know that if we rotate this screw by one revolution, then this load W is raised by a distance equal to the lead of this thread. So, if we move on this inclined plane by a distance 2 pi r, which is equal to 1 revolution of the thread, then the load is raised by a distance of the lead of this screw. So, this inclined plane represents an equivalent of the thread. So, this moment, that is PA, is applied in order to raise this load W. So, we have to represent that by an equivalent horizontal load Q, which is used to raise this load W. This load Q can be found by considering the top view of this screw and the lever. This force P is applied at a distance of A and if this circle represents the circle corresponding to the mean radius of the screw, then this force Q is being applied at a distance of R. So, since we are equivalent diagram we have considered where the moment of this force Q has to be equivalent to the moment of this force P. So, we have this Q dot R equal to P dot A. This angle theta is the lead angle of the screw, and from this equilibrium diagram we see that this reaction force R, which is equivalent to this frictional force and the normal force, is inclined at an angle of phi s for the impending slippage case where the block impends to move upward, and this angle theta is nothing but the angle between the normal to the inclined plane to the vertical axis. So, now the problem of analysis can be converted to a problem of analyzing this inclined plane to find the required quantities. So, this diagram represents for the impending motion upward where this force Q pushes this weight against the slope, and if the thread is a self-locking thread, then if we leave the load on the inclined plane, it will not slide down. So, that is the equivalence to a self-locking thread. So, that means we need to apply a force Q in order to push this load down the incline, and we can consider this free body diagram and find the required force Q and thus in turn the required moment in order to lower the load. Here we see that this angle of friction phi s is greater than this angle theta, which is nothing but the lead angle of the screw. If the thread is not a self-locking thread, then we need a moment that has to be applied to the screw so as to keep the load in the position. If that moment is removed, then the screw will unwind and the load will be lowered. So, we have to find the corresponding load Q for this inclined plane analogy that will resist the load from moving down the incline. So, here we see that this angle phi s is less than the lead angle. So, once we know this Q, we can find the required moment to keep the load in the position. So, let us use this analogy of the inclined plane to solve some problems on square threaded screws. Here you see an example of a clamp that is used to hold blocks when some work is being done on those blocks. So, the diameter of the screw is given as 10 mm, the pitch is given as 2 mm, and the coefficient of friction is given as 0.3. If a torque of 40 newtons is applied in tightening the clamp, we are interested to determine the force that is being exerted on these blocks, and in the second case we are interested the torque that is required to loosen this clamp. So, before we proceed, let us find the lead angle and the angle of friction so as to construct the analogical inclined plane for this screw thread. So, we know the lead is twice the pitch because it is a double thread. So, the angle theta, which is the lead angle, is equal to L by 2 pi r, which is equal to 2 times the pitch, which is 2 mm in this case, and r is 5 mm. So, we have tan theta as 0.1273 and the coefficient of static friction is given as 0.3, from which we can find this phi s. We find theta as 7.3 degrees and phi s as 16.7 degrees. Now, let us construct an analogical inclined plane. So, this plane has a lead of 4 mm and this is the lead angle which we have found as 7.3 and this is the angle of friction phi s, which we have found as 16.7 degrees. So, when we apply the moment, it is represented by an equivalent force Q on this inclined plane, which is used to raise this weight. In this case, this W is the force that is being applied on the blocks. So, knowing the moment, that means we know what is Q, we are interested in finding the force on the block or the clamping force on the blocks. We have already seen that this phi s is greater than theta, and so the free body diagram of the inclined plane will have the reaction force R inclined to the normal face by this angle 16.7 degrees. So, we have QR as 40 Newton meter, which is the applied torque. Knowing the radius of the thread, we find the equivalent load Q on the inclined plane as 8 kilonewtons. Now, from this diagram, we relate this W and Q. We know that tan of this angle, that is tan of theta plus phi s, is equal to Q, the horizontal load, divided by the vertical load W from this force triangle. So, we have this W, we have the horizontal force Q, and the resultant of the normal reaction and the frictional force, that is R, and this angle is equal to theta plus phi s from the diagram. Now, we know Q, we know theta, we know phi s, so we can determine the load that can be raised, or in this case the clamping force, which is equal to 17.97 kilonewtons in this case. Next, we are interested to find the moment that is required to loosen the clamp. So, this is equivalent to lowering the load in the inclined plane. So, this diagram shows the load being lowered on the inclined plane. This angle theta is the lead angle of the screw, and in this case the resultant of the frictional force and the normal force is this R, which is acting on the left side of the normal of this inclined plane. This angle again for the impending case is the angle of friction, which is equal to 16.7 degrees, and this angle is the lead angle, which is 7.3 degrees. So, again we construct this force triangle. This is R, this is W, the clamping force, and this is the force required to lower the load. And this angle from the diagram is phi s minus theta. So, now we can relate this horizontal load Q to the clamping force or the weight of the block in this inclined plane analogy as tan of this angle, that is phi s minus theta, is equal to Q by W. Now, we know the clamping force that is existing. So, from that we can find the horizontal force required to lower the load, or in other words the required moment to loosen the clamp. So, this force Q is found as 2.975 kilonewtons. The moment that is required is equal to Q times the radius of the thread, which is 5 mm in this case. So, we find this torque as 14.87 Newton meter. So, this is the torque that is required to loosen the clamp. So, in the problems, when we use this inclined plane analogy, one has to be careful in drawing the equivalent inclined plane diagram and representing the forces. So, let us see one more problem, so that you become conversant with this method of using the analogical inclined plane. So, here you see a worm gear which resists the rotation of this big gear that you see in the picture. So, this worm gear is being supported by the bearings, and this big gear is supported on this shaft. So, this large gear is subjected to a torque of say 1100 Newton meter, and this worm gear prevents the free rotation of this large gear. So, the geometry is given, that is, you know the mean radius of this worm gear. So, worm gears have these square threads which match with the threads of this large gear, and the coefficient of friction is given as 0.12. So, we are interested to determine the torque or moment that has to be applied to this worm gear shaft, so that the large gear can rotate in the clockwise direction, that means in the same direction of this 1100 Newton meter. We can neglect the friction in the bearings, say let us say this A and B are the bearings supporting the worm gear shaft, and C is the bearing on this shaft. So, we see that even though this 1100 Newton meter torque acts on this large gear, because of the friction existing in the worm gear and the large gear contact, the large gear is not rotating, and so in order to make it rotate in the clockwise direction, we need to provide additional moment to the worm gear shaft. So, let us see how to determine this moment. So, in order to construct an equivalent inclined plane for this problem, let us see this diagram carefully. This torque, that is 1100 Newton meter torque, that is being applied to this large gear, applies a vertically upward load on this shaft because of this gearing. So, it is equivalent to represent let us say this is the applied moment M to the worm gear shaft. This 1100 Newton meter torque applies a vertically upward load on this worm gear, and this force can be found by knowing this moment arm, which is nothing but the radius of this large gear, which is 400 mm. So, we have this force as 1100 divided by 0.4. Now, this problem is equivalent to an inclined plane with this as the load to be raised or lowered on the worm gear face. So, this is the worm gear tooth face. So, now let us draw the equivalent inclined plane. So, this is the lead angle which can be found from the lead of this worm gear. This is the load that has to be raised or lowered, which in this case is equal to 1100 divided by 0.4. And if we see the effect of this moment is to rotate this gear in the clockwise direction itself. So, that means we are interested to move in the same direction of the load that is being applied on this worm gear. So, it is equivalent to lowering the load on the inclined plane. So, this force Q represents the equivalent force that causes this moment M. And from the coefficient of friction, we know this angle of friction for the impending motion, which is 6.84 degrees, which can be found from these equations, that is tan theta equal to lead divided by 2 pi r, and tan of the angle of static friction is equal to coefficient of static friction. Now, once we have created this equivalent diagram, we can write the force equation. So, this equation comes from this force triangle, where R is the resultant force, this W is the weight that is being raised or lowered, and this is the force Q that is being applied to the block in order to lower the weight, and this angle is phi s minus theta. We have seen that when this moment is not applied, the larger gear does not rotate. That means, it is a self locking gearing pair, and so we need to apply this load Q in order to lower this weight or in order to rotate the large gear. So, from this we get the value of Q as W times tan of phi s minus theta, which is found as 219.8 newtons. So, this force is equivalent to a torque of Q times R, which is the mean radius of this worm gear, which is 0.05 meters in this case. So, we have the torque calculated as 10.99 Newton meters. So, this is the torque that is required to make the large gear rotate in the clockwise direction. So, these problems illustrate the method of using the inclined plane analogy for solving the problems of square threads